Consider these objects: a book resting on a table, a curling stone sliding with constant velocity across a frictionless surface, the rotating blades of a ceiling fan, and the wheel of a motorcycle that is traveling along a straight path at constant speed. For each of these four objects, the linear momentum, P, of its center of mass is constant, and its angular momentum, L, about its center of mass, or about any other point, is also constant. We say that such objects are in equilibrium. In this chapter, we are going to look specifically at objects that are in equilibrium when the constant momentum and angular momentum is both zero. We say that object is in static equilibrium. A static object is an object at rest, not like static on an old television set. So of the four objects we looked at, the book, the curling stone, the ceiling fan, and the motorcycle, the book is the only one that is at static equilibrium. It has no motion at all, either translationally or angularly. It is completely at rest. Whereas the sliding stone had translational velocity, the ceiling fan had angular velocity, and the motorcycle's wheels had both translational and angular velocity. Here we see a collection of photos of many objects that are also at static equilibrium. Remember, for equilibrium, they have to have constant angular momentum and constant linear momentum, but specifically for static equilibrium, that constant has to be zero. So here we see in all these pictures, nothing is moving linearly or angularly. If we take a look at Newton's second law for both linear motion and angular motion, if angular momentum, L, and linear momentum, P, are constant, that means their derivative with respect to time is zero. So in other words, the net force, the sum of all the forces, has to be zero, and the sum of all the torques also has to be zero for static equilibrium to occur. So requirements for equilibrium, we said already that the vector sum of all the external forces that act on the body must be zero, and the vector sum of all the external torques measured about any possible point must also be zero. And then for static equilibrium, the velocity, both linear and angular, must also be zero for it to be in static equilibrium. So if we limit our problem to the XY plane, then we don't have to worry about forces in the Z or torques in the X and the Y. And we can simplify our expressions to sum of the forces in the X equals zero, sum of the forces in the Y equals zero, and forces in the XY plane create a torque in the Z. Remember using the right-hand rule. If a torque is in the XY plane, the vector that describes it is in the Z direction. So we say the sum of the torques in the Z is also equal to zero. And let's not forget that the torque has to be zero about any reference point. Sure, because if there was a net torque about any point, then there would be rotation about that point. Let's check our understanding. The figure gives 6 overhead views of a uniform rod on which 2 or more forces act perpendicularly to the rod. If the magnitudes of the forces can be adjusted properly, but not made to be zero, in which situations can the rod be in static equilibrium? So we're going to simulate this. Here's my uniform rod, and these force vectors, I'm going to simulate that by pulling on them with a spring. Okay? So by pulling on a spring, it exerts a force on the rod. So the first one is like that. So I think it's fairly obvious that if I put any tension in these springs, the rod rotates. So in this configuration, there's no way that can be at static equilibrium. Certainly, if I put 2 springs over here, the same thing. As soon as I put tension in them, the rod rotates.
So A and B cannot be at static equilibrium. How about C? Like that. I'm going to use the holes in the board. I'm going to stretch the spring so that there's some tension in the spring. Without this spring, I'm holding it in place with my fingers. If I take that spring away, you see it wants to rotate that way. If I put just enough tension in the spring, it stays at equilibrium. If I put too much tension, it starts to go that way, and not enough tension, and it starts to go that way. But I can get this to be in static equilibrium. There we go. So C works. How about D? Well, I think you can see that D is very much like this situation. We've just added a spring to the right, but just to prove it, let's try it. Pulling in the downward direction. There's no way that it's going to just rotate like that way. Okay, so now let's try E. There's E. E works just fine. And how about F? There we go. We got it. So C, E, and F work.
In nearly every diagram and problem we work, weight will be one of the forces that we have to deal with. So to deal with weight, we must understand a concept called center of gravity. The gravitational force on a body effectively acts at a single point, and we call that point the center of gravity of the body. In other words, we can say that all of the weight of a body acts at a certain location, and that location is at its center of gravity. And if the strength of the gravitational field is the same for all parts of a body, then the body's center of gravity is the same as the body's center of mass. So we'll be using those terms interchangeably. If you hear me say center of gravity or center of mass, know that they are the same spot.
The center of mass of an object like this is at its geometric center. So for this, I can just take my ruler, I can draw a diagonal from one corner to the other, and draw another diagonal from the other corner. And where the two lines intersect, that's going to be my center of gravity of this object. What I'll do is I'll just take a nail and I'll insert it into the center of gravity. Now I'm going to take this string that has a weight on it. This is called a plumb bob. Anything I hang it from, this will hang straight down, of course, because of gravity, and that'll show me the direction of down. And now I can see the point about which the center of gravity is directly over, right above that yellow piece of string. If I take the block and tip it, as long as the center of mass stays on this side of the support point, right here is where the block is touching the table, as long as the center of mass is on this side of the support point, the block is going to continue to fall to that side. I'll keep tipping it. You'll notice that as soon as the string passes onto the other side of the support point, that's when the block will tip over.
When something tips over easily, we say it is not very stable. Let's talk about static equilibrium, center of gravity, and stability. When I was pushing on the block before it tipped over, there are two forces creating torque about the axis. We're going to use the point of contact with the table as the axis of rotation. So here's the center of gravity of the block, and that's the spot where we can say all of the gravity seems to be acting, or all of the weight seems to be acting. So there is the force of weight, labeled mg. Here is my r perpendicular to the line of action of the force, so that produces a torque, mg times this yellow line distance here. We'll call it our perpendicular number 1. Then my pushing force of the pen created a clockwise torque that is opposite in direction to the torque produced by the weight. And this force times lever arm distance number 2 produces a clockwise torque. And because the block is not rotating, I know that those torques add to 0. One is positive, one is negative. They're equal and opposite. They add to 0. However, if I push the block far enough, now the weight is on the other side of the support point, on the other side of the axis of rotation. I've stopped pushing on the block up here, but the weight is producing now a clockwise torque, and that causes the block to tip over.
Stability. For something to balance, of course, like we mentioned, the center of gravity of the object has to be above the base. Not only this way, but also this way. And the higher up the center of gravity is, the less stable the object is. I'll still balance it on a thin edge, but I won't make it so high. Now I can tap it. You'll see it wobbles a little bit, but it doesn't tip over. Compared to this, just the slightest touch and it tips over. Of course, if I put it this way, that's going to be the most stable of all. The center of gravity is very low and the base is very large, and I can't tip that over.
Objects that tip over very easily with just a small force that disrupts its equilibrium, we call that unstable equilibrium. And then objects that return to equilibrium even after experiencing a force, we call that stable equilibrium. Lots of times things that have stable equilibrium have a very wide base, so it's very hard to tip them over. And the wider the base and the harder it is to tip them over, we say the more stable they are.
Back now to England for a look behind the scenes at the London Transport Works at Aldenham, Hertfordshire, to see just one of the demanding tests that buses have to undergo today to prove their roadworthiness. The buses are in fact as safe as houses, but for practical reasons, the main stability test is carried out with about 2 tons of sandbags strapped to the upper deck to represent 30 10-stone passengers. London Transport's 10,000 buses are completely stripped down and overhauled every 3.5 years, although the stability test is only applied to 1 bus of each type, or a bus that has undergone any alterations. Notice that the bus is not secured in any way, and 2 rubber buffers on one side act as the only safety device in case the bus should tip over. The rig is operated by foreman Charlie Taylor, who's been working on bus maintenance since 1927. For the technically minded, the bus is tilted by a hydraulic ram of 1.25 tons pressure. Ministry of Transport regulations stipulate that a double-decker bus must be able to tilt to 28 degrees without turning over, but the engineers test the bus to its limit. Worth remembering next time you grip the edge of your seat when the bus turns a sharp corner. The side dial indicates the angle of tilt of the chassis, while the front dial shows a body tilt of 34 degrees, illustrating the amount of spring deflection in excess of the chassis. Mind you, a bus wouldn't tilt like that going around the Leaning Tower of Pisa, but it's nice to know that it wouldn't tip over if it had to make the trip. If you're still not satisfied, let's conclude with a quick visit to the skid patch at Chiswick Works to show how, even in an uncontrolled skid, the bus remains upright. a tribute to perfect design and another guarantee of the safety of London's famous buses.